We'll continue with this module 7. In the last part of the module, we discussed about torsion and what are the different the theories are there for analyzing the reinforced concrete and the torsion. And now we are going to focus in this module specifically on IS 456 provisions for torsion and how we can design using this IS 456 provisions. We will illustrate them with a couple of examples, right? So let's see. So expected learning outcome is, of course, to explain the core provisions for torsion, which is existing in IS 456. And the student, after attending this video, should be able to design the RCC members subjected to pure torsion or torsion combined with, sorry, shear and flexion. Okay, right. So let's see longitudinal reinforcement. So this is class 41.42. It was developed based on the skew bending theory that we discussed about. You remember we had talked about three failure modes: mode 1, mode 2, and mode 3. And mode 2 is a lateral bending failure mode, and mode 3 is a negative bending failure mode, and mode 1 is a modified bending failure mode. So let's see. So the effective bending mode, what is it? We also derived this expression, right? So how you get this effective bending moment? Torsion is actually converted into an equivalent bending moment. Okay, in this using this equation which we have seen, Tu into 1 plus d by b by 1.7. Now, we've seen for the mode 1 failure, when you have some amount of torsion along with bending, where bending is substantial, then the presence of torsion is going to skew the failure surface. It is going to modify the bending failure, but still you will have compression at the top and tension at the bottom. That is your modified failure. So the code is accounting for this by designing for a moment ME1. You can see that MU is a flexural moment that you get from your analysis. And in addition to that, what the code is saying that now I'm having additional tension at the bottom, right? So that I have to account for them by converting the torsion into an equivalent bending moment as MT and add them to the demand, and then you design it like what you do for flexion. So that is your ME1. So still you have compression as for this failure mode, compression at top and tension at the bottom. So you are adding some additional steel, okay, to account for torsion. Okay, so this is ME1, which is calculated with actual bending moment at the section to give equivalent bending moments ME1. Okay, this is the first one, ME1. Okay, so this is we need to account for. Okay, and the flexure, if the flexural moment is causing compression at the top, ME1 is also going to create compression at the top. Now the value of you can have a situation that this ME1 will be larger than flexural moment because of the torsion, because you're adding to it. Okay, so ME1 will definitely will be larger than your MU in this case. Okay, so because your MT is now a positive value that you are adding to the flexure demand that is already existing, so ME1 will be larger than the flexure demand. So we end up providing more steel on the tension side. Now you can have another scenario like we talked about, because torsion induces tension along the entire periphery. If my bending moment is very small, I can have a situation that at the top also I can develop significant amount of tension. Now code is saying that you design for that. So how do you design for that is when MT become larger than MU, okay, what the code is saying is, okay, now you're going to have a situation that you're going to have a lot of tension that is equivalent to having a negative bending failure. That means I'm going to have developed tension at the top, right? Tension at top. Okay. So the code is saying that so you design by calculating for MU2, which is MT minus MU. When MT becomes larger than MU, there is going to be MET moment that will come. This I need to design only when MT becomes larger than MU. Otherwise, ME2 I don't need to design. So this will happen when your torsional moment is substantially high and the failure may occur by concrete crushing at the bottom and yielding of the steel. So it's equivalent to your hogging bending. You have tension at the top. Okay. So to resist this kind of failure, we need to design for ME moment, moment ME2 that generates compression at the bottom and tension at the top, similar to your negative bending failure. Okay. And in this case, for torsion, we say that it is going to develop tension around the periphery. So always longitudinal reinforcement shall be placed as close as possible to the corners of the cross section, and there shall be at least one longitudinal bar in each corner of the ties. So that you resist effectively that shear flow that is going around the cross section. Now let's see what is transverse reinforcement. Again, class 41.43, again based on the provision that we discussed in the previous part of the module. Skew bending theory to resist large torsion combined with small flexural shear, which is mode 2. So when you have a mode 2, the amount of stirrup requirement ASV is given by this, where TU divided by B1 D1 into SP by 0.875 plus VU. So this is actually remains same. This is for shear. Anyway, we do that. Now for torsion, what is that we are doing is we are taking this form of additional demand that we need to account for in our stirrup calculations, right? So we provide these kind of stirrups, okay? And in torsion, again, we said that these kind of side face reinforcement also we need to provide longitudinal bar. Now stirrups also always torsion. The shear flow is going across the cross section. My stirrup has to be a closed stirrup. Open stirrup will not. Open stirrup when you have only on three sides, then the fourth side you will not have anything to resist that shear flow. So in torsion, we need to have a closed stirrup, not a open stirrup. Right. So these are the dimensions. So how to get this? What are this B1 and D1 in these equations? B1 is the center to center distance of the longitudinal bar in the x direction, and D1 is the center to center distance in the y direction along the depth. Right. So and SV is basically the spacing between the transverse reinforcement. So then you can plug into this. Okay. In addition to that, the code is also specifying some minimum transverse reinforcement to resist flexural shear failure. So like what are these things? Again, this is our minimum reinforcement. ASV should be at least greater than tau VE minus tau E tau C. In fact, this should be tau C. So times B into SV divided by 0.87 F. Okay. So there's a minimum amount of transverse reinforcement that we need to put. Now let's say what are the distribution of torsional reinforcement. So class 26.517a, it specifies maximum limits to the spacing of SV of the stirrups. Again, whenever shear crack forms, either to form from your V or from your torsion, you'll say torsion is going to create a spiraling crack, and then the crack width can be quite significant. Then you will have serviceability issues. So to limit that, the code is saying that the spacing has to be limited, and to develop the post cracking torsion resistance, and then to control the crack widths, and then to control the fall in torsion stiffness on account of torsion cracks. We know that after cracking, torsion stiffness drops quite significantly, but by providing these kind of closed stirrups and longitudinal bar, then we can control that fall in torsion stiffness. So what are the spacing limits? SV should be less than x1 or x1 plus y1 by 4 or 300. Now what are x1 and x1 and y1? That we will see. What is x1 and y1? Now x1 is not to the center of the outermost longitudinal bars. Now it is to the stirrup. Okay, so x1 is coming from the center line of the outermost stirrup to the outermost stirrup. Right. Similarly, y1 is along the depth direction. What is the center to center distance from the stirrup? The center line of the stirrup is what we call here as x1 and y1. And when D becomes more than 450 millimeter, then we also need to put some side face reinforcement. What is the amount of the side face reinforcement? It is actually 0.1% of the web area, very limited reinforcement. It's always a good practice to put some distributed steel for torsion, because as again we are explaining, shear flow is going around the entire cross section, that is going to create some tension. To resist that is always a good practice to put some distributed steel. Okay, unlike in flexure, we put steel only wherever tension is required on only one side, but here in torsion, you need to put steel all around, especially when the depth becomes more than 450. You need to put some nominal amount of side face reinforcement. That amount should be greater than 0.1%. It's a very small amount of percentage of web area, and this has to be distributed equally on two faces. Okay, and spacing is minimum of 300 mm or web thickness. So the spacing between this reinforcement also should be limited to either a minimum of 300 mm or whatever may be the web thickness. Okay, now let's see the design examples. Okay, so we're going to look at first case is a simple RC beam which 250 by 400 mm dimensions. which is subjected to an ultimate torsion moment of 40 kilonewton. So this value you may see that it is very small. It's a pure torsion case. You'll find that compared to bending, we talk about 250, 300, 400. This number may look to be very small for you. But if you see the amount of stirrup requirement, you'll find that the moment you are designing for torsion, your stirrup requirement spacing will become very tight. Your 8 mm and 10 mm stirrup may not work. You have to go for a larger diameter. So let's see. So you're going to use M30 concrete and Fe415 grade of steel. So let's see solution. And these are your dimensions that are given to you. I'm assuming 50 mm effective cover all around the corner. So your effective depth works out to be 400 minus 50, which is 350 mm. And what are the demand? TU is 40 kilonewton meter. Now let's see torsion design for longitudinal reinforcement. So in this case, we're converting the torsion into an equivalent bending. So how do we do that? We derive this expression TU multiplied by 1 plus D by B by 1.7. So you plug in these values, then you get MT. See 40 of torsion. Now you see it converted it to 63.52 bending moment. If I'm designing the torsion as an equivalent bending moment, you have seen that 40 has become 63.52. So the moment value is higher than the torsion that what was given to you. Now you see this is an equivalent torsion. So this is a pure torsion case. You don't have bending demand in this process. It's a pure torsion case. So that is the reason. In this case, MT is there, and you have to design for ME1 and ME2 will be same, which will be MT plus or minus MU. And this works out to be 63.52 kilonewton meter. That's what we have to design in pure torsion. And you'll find that MT is now greater than your MU, where MU is 0. So you have to design for both ME1 as well as ME2, right? So that both of the magnitude is basically 63.52. And from our flexural calculations, we can find your R value, which is MU by BD square. In this case, it is ME1 by BD square. To substitute that, our work out to be 2.07 megapascal. For that, what is the flexural reinforcement? Again, we have to check the limiting moment capacity, and you go back to your flexural modules and find out for Fe415 grade, MU limit by BD square is 0.138 FCK, and that works out to be 4.14. So this demand is less than this, so it is okay. So the sectional dimensions, whatever that we have provided is okay. And then we go ahead and calculate what is the percentage of your tension steel. You remember we developed this quadratic equation in the form of R and FCK and Fy. So you plug in FCK equal to 30, Fy equal to 415, and PT, you know the definition for PT, which is 100 AST by BD. So PT by 100 will be AST by BD, and you plug in the value for R, which we calculated that to be 2.07, and FCK is 30. You'll find that the amount of percentage of tension steel is PT by 100 is 0.0062, PT is 0.62. So 0.62 percentage of tension steel is only required because your demand is slightly less. And you find that the amount of tension steel required is 550 mm square. Right? So we can provide three numbers of 16 mm bars, which works out to be 603. So 201 mm square is your area for your 16 mm bar. Then you put both in flexural tension and compression state. So you see the depth of the member was 400 mm, right? So as per the code requirement, when the depth is more than 450 only, you have to put some sideways reinforcement. So you need to put only 3 bars top and bottom for this steel. Okay. Now let us see what are the transverse reinforcement requirement. Okay. How do you calculate transverse reinforcement? Again, we convert the torsion into an equivalent shear. Now, how do you do the equivalent shear? Equivalent shear is 1.6 TU by B. Okay, is your equivalent shear. Okay, so now if I want to reduce the shear demand from torsion, what is that I do? Providing a wider beam, because B is coming in the denominator, providing a wider beam will actually reduce the shear demand. But for flexure, always we provide more depth. This is a more efficient way of designing. But in torsion, in fact, if you put a wider beam, that is going to reduce your shear demand. Okay. So in this case, anyway, we are limiting B to 250. So if you substitute, anyway, VU in this case is 0. Okay. Because it's a pure torsion that we are designing. Okay. So if you plug in these values, you get the equivalent shear is 3.29 megapascal, and the equivalent shear has to be less than tau C max, which is 3.5 for M30 grade. So you see that you are getting very close to that of this, even for a small torsional moment of 40 kilonewton meter. That's why I said the moment torsion comes, your stirrup requirement will go up. In fact, if tau E is coming to be higher than 3.5, then my 400 by 250 section will not work. I have to increase the width or increase the depth. In fact, for torsion, increasing the width would be a better solution, right? So tau E is less than tau C max. The cross sections are adequate to prevent brittle compression mode, so it's okay. Then we can calculate what is the PT. Why I'm calculating PT here? Because I have to use it to calculate tau C, right? So tau C is 0.85 square root of 0.8 FCK into this. You substitute and beta value, maximum of 1 or 0.89 FCK by 6.89 PT. You plug in the value for PT and get a beta value of 5.62, right? So we get this 5.62, and then you put it into this tau C equation, you get a tau C value of 0.542 megapascal. You see, my demand is 3.29 and concrete is giving me only 0.542, roughly 1/6 of what I need. Remaining 5/6 I need to get it from stirrup. So even you have a very small torsional moment of 40 kilonewton meter, the shear demand is quite significant. So that is the point what I'm trying to emphasize. So torsion can shoot up your stirrup requirement quite a bit, right? So if you see tau C has become less than tau E, so torsional reinforcement is required. Then we go ahead and assume a 12 mm bar. So generally, it's not a good practice to put 12 mm stirrup. Okay, we have talked about it, right? Either you use 8 mm or 10 mm max. But in this case, because torsion is there, otherwise my spacing will become too close. So then I cannot do the concreting. So that is the reason I'm using 12 mm a 2-leg stirrup. So ASP will become 2 into pi by 4 12 square. So that works out to 226 mm square ASP. And then spacing requirement, we know that it is 0.87 Fi times D1 into ASP by this is your shear demand. So if you substitute that, you get B1 is center to center of a longitudinal bar. So that works out to 50-50. We have said effective power for longitudinal bar. So 400 minus, sorry, 300 minus 50-50. It works out to be B1 is equal to 200 and D1 is basically 400 minus 50-50, which is 300. So you plug in these values, Fy is 415, D1 is 300, ASP is 226 mm square, and shear demand is, now we are talking about pure demand, so we use 0. So there is no other additional component. Now you see in this section with 40, if you have another shear demand, then again your spacing requirement will go down like anything. So you have to put very close stirrups, okay? So that you have to keep in mind. So it works out to be 85 mm. Okay, so 85 mm stirrup. For pure torsion of 40 kilonewton meter, for a beam of this dimension, you need to put stirrup of 12 mm stirrup of 85 at 85 mm spacing. 85 mm spacing, if you see, it's not too long. It's very close spacing. It's like basically you've created a kind of a steel tube inside the column. That is the reason. So you also see again we are using 12 mm bar, or even for 12 mm bar I get a spacing of 85 millimeter, which is very tight spacing. Now let's check for minimum spacing. So you plug in this minimum spacing equations, then you work out to be 118.87 millimeter, and then we should also have one more equation that we need to satisfy, which should be x in terms of x1 and y1. So x1 is basically 200, right? And then in addition to this B1, okay, this is B1. I add longitudinal bar, one longitudinal bar, which is 16 plus one stirrup diameter, which is 12. So it works out to be 228 millimeter. Similarly, x1 plus y1 by 4, it works out to be 138 mm, and then 300. So you have to take the minimum of this, which works out to be 139 mm. Anyway, what we are providing is 85 mm, which is less than 139 mm. So which is okay, right? So we can provide 12 mm bar at 85 mm on center for transverse reinforcement. So the overall detailing works out to be this pure torsion. So you need to provide reinforcement for the entire length of the member, right? And you put two leg to 12 mm bar dia at 85 mm center. So the 85 usually what we do is we try to keep the spacing as a round number, but already my spacing is very tight, 85. That is the reason 85 I'm not reducing or 275 or so. Then it will become too tight. Then concrete, if you're using 20 aggregate, then the concreting will become difficult. That is the reason I'm not changing the spacing. I'm keeping it at 85 only. Now you can see here this dimension is 400 So if this D has become more than 450, then I need to put some side face reinforcement also. It's actually a good practice. Even though this is 400 I can put some very nominal side face reinforcement also. So that could be, say, basically I can put two 8 bars on each side. That will be good practice. So that will help in controlling the crack width. Okay. So this is all good detailing. Detailing is also very important. Right. So this is the overall section detail. In fact, this is optional. Okay. The side face reinforcement is required only when D is 450, more than 450. But because we are dealing with pure torsion here, so I can go ahead and put some nominal steel of 8 bar at certain minimum spacing, just to in case if you have spiral cracking form, that reinforcement will help in controlling that crack width. Right. Okay. So this is for first example where we dealt with pure torsion. Now let us look at next case, example 2. We have an RC beam section which is 300 wide and 750 deep, and it is subjected to an ultimate, that means factored demand of 145 kilonewton meter. And see, this beam is also quite deep, so that's and but the ultimate twisting moment of 145 kilonewton meter, and it is also combined with a sagging bending moment of 150 kilonewton meter and a shear of 90 kilonewton. So now you have all the combinations. Now let us see how to design this. So they are saying that okay, you take M25 concrete and Fe415 grade. Okay. And for bending, you can go for 500, 550 grade also. Okay. But when it comes to stirrup requirement, code is even if you're using 500 or 550 grade, in my calculations, I have to use Fe415, right? So that you have to keep that in mind. So these are the input parameters that are given to you. B is 350, depth is 750, FCK is 25, Fy is 415, and torsional demand is 145, flexure demand is 150, shear is 90, and you're going to take 50 effective cover for all around the corner, and your effective depth is 700 millimeter. Okay, assuming 50 cover. So design of longitudinal bar. So MT that we are converting that, again, what is the first step? We convert the torsion into an equivalent bending moment, as we have derived this equation previously. So when you substitute 145 and then plug in these values, you will find that the equivalent bending becomes 268 kilonewton meter, which is higher than your torsion moment of 145. In fact, one way again, for torsion, if you want to have an effective design, if you reduce or if you provide more width, then that is going to reduce your demand, right? So, but for bending, always we put more depth to create an effective design. But in for torsion, in fact, if by increasing the width also, you can end up with a very effective design. So that is the one. So this is your equivalent bending. So now for ME1 and ME2, we have to check for both. So ME1 is 268 point plus 150, that works out to be 418, which is going to create flexural tension at the bottom. Now you find that MT is greater than MU, which is 150. So I need to definitely design for ME2 as well. So ME2 is MT minus MU, and that difference is working out to be 118.6. That is going to create flexural tension at the top. Again, why? Though bending is going to create compression, now the tension that is created by torsion now is going to nullify that compression from bending and going to put additional tension on the top. That I need to account for that. That is why the ME2 is coming. Okay, so this 118. So we go and design for bottom steel. Again, we calculate your R values, which is 418 divided by sectional dimensions. It works out to be 2.43 megapascal, which is less than your MU limit, which is 3.47 megapascal. Then go ahead and calculate your PT, which is a percentage of tension steel. And this, we have derived this in the form of a quadratic equation. So you plug in for your FCK and Fy and R values, then you get PT as 0.0077, or in other words, it's 0.78 percentage. It's a very, very small percentage of steel, less than 1 percentage. And it works out to be the area, because the area of cross section is quite high, that works out to be 1892 mm square. So we can provide four numbers of 25 mm bar at the bottom, which is 1963. Now see, I don't need to put the same amount of reinforcement. You can do torsion. What we did was same thing that we put for ME1 and ME2 are same. Now ME1 and ME2 are here. In this case is different. So my top reinforcement is governed by ME2. So let's say top steel. Now I get in my R2 as very small value of 0.68. So which is again, we have already checked that it is less than ME limit value. And PT can be calculated from this. We'll find that that works out to be about only 0.19 percentage of steel, very small amount of steel. That works out to be 480 mm square. So I can say minimum, again we have to check for this minimum amount of tension steel, and that works out to be 500. So anyway, we can go ahead and put 3 bars of 16 mm. That works out to be 603 mm square. So now we calculated what is the top longitudinal steel and bottom longitudinal steel. Now the beam is 700 mm deep, which is more than 450. So the code is wants us to put some side face reinforcement. That side face amount reinforcement works out to be 0.001 BD, or 0.1 percentage of your web area, which is B into D. That works out to be 263 mm square. So you can put six numbers of 8 mm bar, that is 300. So it's a very small amount of small diameter that you put, and you're not going to increase the cost much. It's a very good detailing approach. Okay, so you put 3 on each side of 8 mm bar, then the vertical spacing between the longitudinal bar also should be less than 300 mm. Anyway, because you're putting 3 bars, it will work out to be okay. So now we have done the longitudinal reinforcement. Now let's see how to design the transverse reinforcement. So again, we convert the torsion into an equivalent shear by 1.6 TU by B, and we calculate your equivalent shear stress as 3.07 megapascal, and which is less than 3.1, just adequate. In fact, this value, if it is going more than 3.1, what we should do, this dimensions will not be adequate. We have to increase the dimensions to satisfy that tau E should be less than tau C max. Again, why is this limit put? We don't want concrete to fail in shear compression. So code is prohibiting you from designing sections that is going to fail in shear compression. It will be a brittle mode of failure. So we are going to limit your tau E to be less than tau C max. Right? So again, to calculate tau C, PT value we calculate, that is to be tension steel, which is 0.8. Then you plug into your tau C equation. Then you get tau C value of beta value is 4.03. Again, I go ahead and put beta in the tau C equation, and then you get tau C value of 0.564 megapascal. You see again, concrete capacity is very, very less compared to that of what I required for your shear depth. So all the extra things that should come from only stirrups, right? So torsion reinforcement is required. And then again, because my requirements are high, so I'm going to use 12 mm bar 2 leg stirrups. So ASV, what I'm going to have is 5 by 4 12 square multiplied by 2, that is 226 millimeter square. And then you plug into this equation to get your spacing. SV is 0.87 F by D1 into ASV by TU by B1 by BU by 2.5. So if you substitute and calculate the values for B1 and D1, which we have done previously, B1 was 250 and D1 was 650, right? And B1 and D1 are center to center distance between the extreme longitudinal bars in the X and Y direction. So you get SV value as this, which is 86.17. Again, you find that the spacing required is very, very small, only 85 mm, right? So again, we go and check for minimum spacing. So if you see that SV required for minimum spacing is 93, and then next to provision X1, 287, X1 plus Y1 by 4 is 242, and 300. So in all of them, the least is basic. What we are giving here is 93 point. So 86 is less than all the other requirements. So we can go ahead and put 12 mm bar at 85 mm on center, right? So finally, if you look at the overall detailing, you'll find that this is governing from ME2, this is governing from ME1, and this is your side face reinforcement, right? And then your stirrup. Stirrup is placed at 12 bar at 85 mm. So you can see the moment you have torsion coming for a design, your stirrup requirements are increasing, and more often when MT becomes higher than MU, you need to put steel on the compression side as well for that, right? So these are the things that we have discussed. And then when the depth is becoming more than 450, it's good practice. It code wants you to put some side face reinforcement as 0.1 percentage of your web area. In this example, it works out to be three numbers of 8 bar on both sides. So total 6 bars. Right. So with this, we're completing this. So what we have discussed is IS 456 provisions for torsion design. And we also took two examples. First example was RC member subjected to pure torsion. And we find that even though it was 40 kilonewton meter, we found that the stirrup requirement or longitudinal reinforcement requirement was quite substantial. Then we also looked at another example where we looked at design of members subjected to combined torsion, shear, and flexure. Again, the presence of torsion was designed by converting into equivalent bending and equivalent shear, and then providing adequate detail. Right. So these are some of the references that you can look at it for additional information on torsion. And again, the slides of this module was prepared by one of my PhD student, Mr. Muttaraja. I would like to acknowledge his help. Thank you. So we'll see you in the next module.